So for the rest of this chapter, we're going to start investigating power series. So we talked about sequences and then series. And series were just these, the sum of an infinite sequence. So a power series is basically just a series, but where you can plug in different x's, right? And then get values. So you're using the ideas that we've already introduced from series to define functions. And so we can define a power series like this, or I'll just write it out. So a power series looks like this. Okay. C sub n x to the n. So the C sub n is some sequence, and then we just have a fixed x, right? That'll be like it'll be a variable in some sense, but it'll be like f of x equals this, where you can plug in different x's to get that. And so if you just plug in x cubed and so on. Okay? So you don't have to bother writing anything down, but what do you think you get if you let x equal 0 here? You plug 0 in for x, what's the answer?
0.
Or 1.
Not 1, but C0, right? Whatever this is. Whatever that first constant is, right? So you're always able to plug 0 into this. And then depending on these CNs, you can plug other x's in. Okay? And so we'll say this one's centered at 0, because 0 always works. It's always going to be defined there. But if you move away from 0, you may run into problems. Okay? And so that'll be what today is all about. We also have power series centered at a different place. So rather than just x to the n, we'll have some fixed a, and you'll look at a power series in the form x minus a to the n, c sub n is. And so that's, again, c0, c1, x minus a, c2, x minus a squared, and so on. Does that make sense? And so for the most part, when we do stuff with power series, we're almost always going to be working with just this first form, but most of that's just for convenience because it's easier to write things like this. We'll have a few examples where we sort of move into the messier territory, but we just say here, this one is, let's write it this way, centered at x equals a. And so for this one, when you plug in 0, you may not get something that's nice, right? Because you get c1 times a, c2 times a squared, well, negative a squared. But when you plug in a, you'll get 0 here, 0 here, right? So it always will work at a, and then the question is what happens if you leave a and go elsewhere. Okay? So we can already do a bunch of stuff with this just using things we've done before. So let me just give you an example, and then we'll define some stuff here in a minute. For what x does, and so I'll just write down a power series here. Here, we'll do a couple of these. So x to the n over 3 to the n. So again, don't get too bogged down by the x. The idea is that the x is just some variable, right? So you can plug in different x's, and we're asking for which x's, when you plug them in, do you get something that converges? Well, the whole last several sections were devoted to figuring out when things converge or diverge, right? And this one, this series here, has a bunch of exponentials, right? X to the n, 3 to the n. So what was the test we used to determine if series with exponentials in them converge or diverge?
A ratio conversion.
Ratio test, right? Okay. So we're going to apply the ratio test. So I'm doing this a little bit before we actually introduce some of the terminology, but this is your method whenever you see these. So you'll see this question a lot. It's eventually going to say, find the interval or the radius and interval of convergence for this. We're going to do it without that terminology, then we'll add that terminology. But here's your steps every time. So apply the ratio test. Take the limit as n goes to infinity, absolute value of what? x to the n plus 1 over
3n plus 1.
plus 1 times,
3n over x to the n.
okay, good. And again, a lot of times these are real simple, a lot of stuff's canceled right away, so this is no different. What is it?
X4 over 3.
Okay, good. And this time, we don't know what the x is, right? It could be negative, and so I'm gonna leave the absolute value around it there. Okay. So, we just had the ratio test on our last exam. What were the conclusions? If that limit equals something, if it equals 1, the test fails. If it's bigger than 1, divergent. If it's less than 1, convergent. Absolute convergence. So, this thing is going to fail when it goes to 1, and so we just figure out where the test fails. We set that limit, and I should say, there's no ends left in this, right? So that's the limit, it's just this. And so we set that equal to 1, that's the cutoff where it fails. If x is bigger than what we find here, it'll diverge, right? Because then that limit would be bigger than 1. And if it's less than, if x is less than whatever we find here, it'll converge because you'll be inside there. And so what's the solution to this? Absolute x equals 3. That make sense? So plus and minus 3 is the sort of cutoff spot that we're looking at. And so this series diverges, oh, sorry, converges on, well, I'll just write it this way. The interval from -3 to 3, right? That's when absolute value of x is less than 3. Diverges on -infinity to -3 and 3 to infinity, and at x equals 3, x equals -3, we don't know, right? There's a question mark, that's where that test fails. That make sense? And so we're going to test those endpoints separately. So now we test, so this is going to be the sort of standard way this flows, right? You'll do the ratio test, you'll solve for that absolute value of x. This is going to be called the radius of convergence. I may as well do that right now. This 3 is your radius of convergence, and I guess as long as I've written that down, let me just say, remember this is a power series centered around 0, right? Because it's just x to the n. And so that radius of convergence means, we already said it converges at 0, right? And then what we've seen here is it keeps converging until you get up to 3 and -3, right? So there's that radius of 3, right? You're in the middle of that thing. Okay. All right. So there's your radius of convergence, and then we need to check these endpoints. So we know it converges everywhere inside, but at those endpoints, this test failed, and so we have to do more. So we check, I'll just write it this way, check your endpoints. Okay. And so let's just do x equals 3. So that's the series of just 1, right? Does that converge or diverge?
Divergence, right?
Yeah, it's 1 plus 1 plus 1 plus 1. That's going to go off to infinity clearly, right? So there's divergence. How about x equals -3?
Converge.
Well, let's look at what it is. Okay. So -3 to the n is the same thing as -1 to the n times 3 to the n, right?
So,
Cancel the 3's. You get -1 to the n. Does that converge or diverge?
Oh, yes, it diverges, right?
Okay. So I think, it definitely diverges, but I think we don't seem super confident in it, so let's talk about that separately. So that series looks like what? When n is 0, you get 1, when n is 1,
Negative
negative 1 when n is 2, or, yeah, 2, 1 again, right?
1. Okay.
Negative 1, 1, negative 1, 1, no, negative 1, and so on, right? And so you got to be careful here, because some people will think, oh, well, that's 0 plus 0 plus 0, right? Oh, that's 0, but that's not the way you need to think of it, because how do we find the sums of these things? You have to do partial sums. So your S1 is 1, right? Your S2 is 0, 1 minus 1. Your S3 is back to 1, right? Your S4 is 0, and so on. So you just have your partial sums just alternate between 0 and 1, and so there's no limit to that. And so you don't have to show any more work. You can just say this diverges, but you should sort of understand that. In particular, negative 1 to the n does not go to 0, right? It goes back and forth between plus minus 1, and so the nth term test tells you it diverges. But either way, you come up with this, okay? And so now we know, right, it converges inside negative 3 to 3, and it diverges at the endpoints. And so now I'm just going to go ahead and define these things in the middle of the problem. The interval of convergence is negative 3 to 3, and again, I'm using parentheses there because it diverged at the endpoints. If I got converge for one of these, then I'd put a square bracket to include that endpoint. Okay, so we'll do more here in a second, but how does that feel? We're okay with this so far? Okay. Here, let's try one more of this. Should be pretty similar. Same directions. Let's do 2 to the n. 2 to the n, x to the n over n plus 1. So take a second, do the ratio test on this one, and then once you perform the ratio test, see what happens. And this one's got a little bit different behavior at the endpoint. So a lot of it will feel very similar to what we just did, but then when you check the endpoints, you'll get some stranger stuff happening. Okay, that's over. Keep working it out if you haven't yet. This is what you should get. It doesn't need to be written in that order. just look at what's happening. Is everybody okay? This first stuff, right, 2 to the n and x to the n cancel. So you're just left with a 2 and an x up top. And so I'll take the absolute value of those, and then I'm just rewriting this as n plus 2 down here, and so I'm just putting n plus 1 over n plus 2. So now, as n goes to infinity, well, 2 and x have no n's in them, so they're just a constant. And then n plus 1 over n plus 2 goes to 1, so this whole thing just goes to 2 times the absolute value of x. Make sense? Okay. And again, this one's going to converge at 0, right? And then our radius of convergence, we're going to figure out where does it go from there. And so all we do is set that equal to 1. 2, absolute value of x equals 1. And so you solve for the absolute value of x. In this case, it's 1/2. Okay? And so I'm just going to start. I'll define this a little more formally later on, but this is whatever that value is, you solve for. So if this is x minus 5 to the n, you solve for the absolute value of x minus 5. It's whatever that thing, that x being raised to. So the radius of convergence, in this case, is 1/2. And now your endpoints will be where?
Negative 1/2, 1/2.
Yeah, negative 1/2 and then 1/2, so check. 1/2, negative 1/2, and so let's just do that. So at 1/2, your series becomes, this time I'm just going to plug in for the x, right? So it's 2 to the n over n plus 1, and so if I replace the x with 1/2, what do I end up with? Yeah, right. 2 to the n times 1/2 to the n. They'll just cancel each other out. So you'll get 1 over 1, or n plus 1, and you said it diverges. So that's good, again, but you don't have to show a bunch of work, but you should give a reason why. Why does this diverge?
Harmonic series.
Yeah. This is the harmonic series. Does that make sense? Then, if x is negative 1/2, you get almost the same thing happening, but a big difference, which is to the n, negative 1/2 to the n, n plus 1. And again, people tend to make a lot of mistakes here in canceling this. A lot of times I'll just get negative 1 over n plus 1. It's not negative 1, right? So it's 2 to the n, negative 1 to the n, and then 1/2 to the n. So the 1/2 to the n and the 2 to the n cancel before. But you don't just have negative 1, you have negative 1 alternating, right? So you should end up with that. Okay. And so does that series converge or diverge? No? It converges because what is it? That was the harmonic series. This is the alternating harmonic series. Right? Or you could apply the alternating series test. So you could just say converges. I think this one's straightforward, right? It's negative 1, so it's alternating, and then 1 over n decreases to 0, so it satisfies all the conditions. So you could just say by the alternating series test without a whole lot of work. And again, I know this semester is really crammed together during the summer. During the regular year, it would have been a couple weeks from when we introduced some stuff until we get to this, and so it would feel like, okay, well now we can just say this by the alternating series test. In this semester, it was a couple days ago, but we still are going to be like, okay, now we know this, and we don't have to show the details, right? So anyways, we end up with that, and so the interval of convergence equals, so it's just like this last one. Remember, our series here started at 0, and so the interval went from 0 out to 1/2, and back to negative 1/2, and then we checked the 2 endpoints. And so this time, so it's from negative 1/2 to 1/2. That's what you'll get once you know your radius was 1/2, right? Your interval will look like this, and then it's just a matter of whether it's parentheses or brackets on the side. So at 1/2 we get divergent, and so that means we use a parenthesis there, right? We're not including 1/2. At negative 1/2 we get convergence, and so we put a square bracket to include that, right? So now we're including that left endpoint, but not the right endpoint. Does that make some sense?
So convergence is a bracket, and then,
Yes.
divergence is parentheses.
Yeah, because it converges for everything inside, right?
Yeah.
And then we want to say it also converges at the endpoint, so that bracket means you include that endpoint.
Okay.
So do we need to write out the interval of divergence?
No, so the theorem, I'm gonna state in a minute. We have an interval of convergence, and outside of it, it always diverges.
Okay.
Because remember, we were using this ratio test, and we said, this is where it fails. Inside it will always converge, outside it will always diverge. And so, if you know the interval of convergence, then it diverges everywhere else. Okay. So, let's just do some real basic ones here just to get this. Okay. X to the 2n over n plus 1 factorial. So we're trying the same thing here. So try the ratio test. Let me point out one thing real quickly. Right? This on the surface has a slightly different form because it's x to the 2n instead of x to the n. But so if we plug in 0, what do we get? X to the 0 equals 1.
Yeah,
1 factorial. Plug in 1. X
that's good.
squared over 2 factorial. Plug in
X to the third.
6
Oh, my bad.
X to the
Yeah,
6th. over.
4 factor.
Oh, are we on? Yeah, 3 factorial, right? Right. When n is,
Yeah,
when n is 3, you get 6 up here and then 4. Oh, yeah, you're right. I was off on this one. There we go. 3 factorial, right? 4 factorial. There we go. Does that make sense? Point is, you're just plugging them in. Now, the only reason I wanted to write this out is, we still consider this a power series, it just has 0 for those other terms that are missing, right? And so it's still a power series, so don't get thrown off by that. This is a power series, so we can play the same thing. Try your ratio test. Be careful. Again, you can show less work if you feel comfortable with all the algebra that's going on here, but let's just do that. So what's that exponent on the top x? It's x to the 2n plus 2, right? And so when you cancel out the x to the 2n, what are you left with?
X squared.
X to the 2n, or x to the 2, sorry. And I'll put absolute value, it won't matter in this case. But just be careful when you see future ones if there's, you gotta do that algebra correctly. And then, again, you could simplify this all at once if you felt comfortable as well, but it's n plus 1 factorial and then n plus 2 factorial on the bottom. So when I cancel those factorials, what am I left with?
N plus 2.
Just n plus 2 in the bottom. So I end up with x squared over n plus 2. Does that make sense? So what's that limit going to be? Remember, x is a variable, but it's a fixed value, right? X could be anything, but if we fix x, what's the limit of x squared divided by n plus 2?
0.
Yeah, right? That x is staying fixed, so x squared is a fixed number, and you divide by n plus 2 as n gets bigger and bigger. So that whole thing goes to 0. So what does that mean?
Converges.
Converges, and it converges for every x, right? No matter what x's we get to. And so we say here that the radius, I'm just going to say radius is infinite. Does that make sense? It converges everywhere. And the interval, most of the time, once we say that, we don't bother with the interval. But technically, you could write out the interval as this. It's just everything. Does that make sense? All right. And then real quickly, let's do the other extreme as well. So we've seen two things, right, where there was a cutoff point at 3, I think it was, on the first one, right? And then 1/2 was this sort of cutoff point, and then we had to check those endpoints. Here's one extreme, there's no cutoff point, it just converges everywhere. And then the other sort of extreme will be this one. Here, well, let's do one that's not centered at 0 as well. Okay. So we'll do one where it's centered at 0, or not centered at 0. We have to check endpoints in a minute, but let's do this one first. I'll let you catch up. Still writing.
Should that one be 2 factorial under the x squared, and the second one?
No, because it's, right, this is n plus 2 times n plus 1, and then it's way down, so I'm just canceling the factorial parts.
Yeah, I mean the top.
Here?
After the equal sign,
I guess I'm confused. Where are we at?
the first one over the x squared over 3 factorial, shouldn't be that 2 factorial? And the second one,
Oh, you're right. I had that right the first time. So 2 factorial, 3 factorial. Is that right? That makes sense.
the one is 4.
No, this is 4, yeah. That's what threw me off. Thanks. X to the 6th, and then 4 factorial. Yeah. Thanks. Yeah, just be careful when you do those. I was trying to be lazy, but if you're asked, if you have to, just, plug in one number at a time and just be real clear what's happening. Right? When n is 1, you get x to the 2 times 1, so x squared. N is 1, so 1 plus 1 is 2. And then n is 2, x to the 4th. 2 plus 1 is 3. Okay. So, you okay with that one then? Okay, so this one, where are we centered on this one? X minus 2. So we're centered at
2.
positive 2. And so this time, whatever your interval looks like will always contain 2, and then you're going to go off in this direction and off in this direction. And it'll always be, you go over the radius, and then you go over the radius this way. So whatever that radius of convergence, in this one it's going to be trivial. But usually, you're centered there, and so you'll pop over in those 2 directions. We'll do one in a minute to show that. But let's try this one. So again, ratio test. X minus 2 to the x plus 1 over
N plus 1 factorial.
n plus 1 factorial, and then
3 to the n factorial over x minus 2 to the n.
very good. And same sort of cancellation as always, right? Which is the 3's and the factorials cancel, and so what do we get? Just
There's an x minus 2 on the top,
and I'll put absolute value around it, and then
3 on the bottom, 3n.
and a 3 and an n plus 1, right?
Okay.
Just the factorial cancels like that. Does that make sense? Okay, and so now if this turned out to be 6, this limit, it's not, but if it turned out to be something, you take the limit, right, and say we ended up with that equals 6, then you solve for the absolute x minus 2. Whatever you were centered around, you solve for that, and then that's your radius of convergence. But in this case, we don't have that. Again, x is a constant. So what is, oh, I put my factorial in the wrong place. Oh. I'm doing the exact same problem I just did. I wanted to put my factorial up top. Here, let's finish this up real quick. 0 again, right? And so what do we have? Radius is infinite, interval is,
Negative infinity, infinity.
yeah. Let's try the same one, the one I actually meant. You look away from your notes for a minute and you forget what you meant right now. 3 to the n, I want the n factorial up top. Okay? So same idea, right? This one's centered at 2, and the algebra should be almost identical. Okay. now the x minus 2 is fixed, what happens as n goes to infinity?
It'll converge. Well,
Yeah, I mean, this limit should, so if x was 4, then you get 2/3 times n plus 1. What does that go to? Infinity. If x was 5, 3/3 times n minus 1, that goes to infinity, right? So this goes to infinity if x isn't 2, right? If x is 2, it's just 0 everywhere, but that's sort of the trivial case. So we have this, and so what would you think, so again, we're centered at 2, it always converges at 2. We've shown it's infinity if you're not at 2. So if that limit from the ratio test is infinite, what's the ratio test conclude then? Well, does the ratio test conclude convergence or divergence if your limit's infinity? Diverge, right? So you have a divergent sequence everywhere except for at 2. So it does converge at 2, it doesn't converge anywhere else, so what do you think the radius is then? How big is the radius?
negative infinity to, or 2 to infinity.
No. It only converges at 2. This is the only place it converges. It diverges everywhere outside of there. The radius is 0. There's no place it converges. And then there is no interval of convergence. I won't even bother writing it down, right? If the radius is 0, it only converges, only converges at 2. And I'll just say, this is a stupid power series, right? It represents when you plug in 0, you get 2. Well, you know what you get. You plug in 0, you'll get 1, 1, 1, right? So you'll get 1, and then after that you'll get all these other values, but if you plug in anything other than 2, the thing's undefined, and so it's not representing a meaningful function at all. Does that make sense? And our point is that we want these power series to represent functions, and so this is just a silly one. So, let me state this theorem quickly. All right, I'm going to do just a very abbreviated version of the theorem, no proof. The theorem just says that if you have a power series that converges for x equals b, then it is absolutely convergent for any x such that x minus a is less than x minus b. So all it's saying is this, right? It's saying we know it converges at a, and it's telling you if you get a b and you know it converges at b, right? Oh, I put an x. I want b minus a here, right? It's saying if it converges at some b, right? And then you take any value that's closer to a than b was, right? So you could take, I'll just write it this way, some a plus some little c, or some a minus some little c. As long as that c, right, keeps your absolute value less than the difference between b and a, then you're going to be absolutely converge in that. It essentially comes down to what we saw with that ratio test, right? That you're always going to have an end point that you sort of can figure out if it converges or diverges in there. So that's why once you know one place of convergence, you know it converges for everything less than it on both sides. And then you might have weird stuff happening at the endpoints, but that's the only place where something strange can happen. Okay? And so this theorem, it follows that this theorem basically says that this idea of a radius of convergence is well defined, that the radius of convergence is defined and r is 0, r equals infinity, or r is some number greater. Essentially just saying, all three of those cases we've seen can happen, right? You can have it converge everywhere, it can converge nowhere except for that one point, or else there's some cutoff point and it converges on everything that's closer than that, within that radius of convergence. And the endpoints need to be tested separately. Okay. So, we're just gonna do the same thing that we were doing. So, find r, well, let's just say the radius and interval of convergence. So exactly the same thing we were just doing, I just have the terminology in here now. For okay, so try. There, I'll put two of them up here. Okay, so take a minute, try to do both of these. I'll tell you, everything we did, the last examples, we kept using the ratio test. That second one, it'll be easier just to use the root test. You could get away using the ratio test, but the root test will give it to you immediately. So I would just use that. All right, I'll give you 2 minutes or so to work on it. All right, so if you haven't had time to finish, that's fine. But let's go through these together. And again, this is where we start waving our hands at some things that we made you show last time. I'll just jump ahead. So it'll be x minus 2 to the n plus 1, right? 3 to the n plus 1, and then n plus 1 plus 2 inside that log, so n plus 3. And then times 3 to the n log of n plus 2 over x minus 2 to the n. All right, so when I cancel stuff off, I end up with an absolute x minus 2. What else do I get? Over 3, and then log of n plus 2 over log of n plus 3. Yeah, and so this is, so last time, right, if we would have seen this log of n over log of n plus 1 or something like that, you could do L'Hopital's rule, right, if you need to find that limit. But if it's linear and it's linear, they're just gonna go to 1, right? Log of something over log of the other linear. This is all gonna go to 1. So this whole thing should just go to absolute x minus 2 over 3. Remember, this guy's centered at 2, right? And so when we find the radius of convergence, we take whatever that limit is, we set it equal to 1, and then you solve for whatever this is. Okay, so absolute x minus 2 is 3, that's your radius of convergence, 3. Okay? Now, you could solve, what does it mean for absolute x minus 2 to be 3? It means x minus 2 is 3, or x minus 2 is negative 3. Right? Or you can just think, if I'm at 2 and my radius of convergence is 3, then I'm over at, to the right I'm at 5, right? And then where am I at to the left?
Negative 1.
Negative 1, right? So just be careful, don't go back to negative 5 or even 3 and negative 3, I'll see that a lot. You're starting at 2 and you go 3 this way and 3 that way to get your endpoint.
So where, in the algebra, how do we get 3, the x minus 2 is equal to 3?
So we just, remember, we're doing the ratio test, the
Yeah.
cutoff is when this equals 1. So we set this equal to 1, and then you solve for the
Oh.
absolute value of whatever was up here.
Okay, yeah, so we always set whatever equal to 1.
Yeah.
Okay.
Okay, and so then check your endpoints. X is 5. This thing becomes, I think I'll start abbreviating here. When you plug in 5, what do you get? 5 minus 2, so you get 3 to the n. It'll immediately cancel that 3 to the n. So that whole thing will be 1 over log of n plus 2.
0.
Does this converge or diverge?
Converge, right?
No.
Yeah.
It diverges. Remember, it's
1 over.
it's bigger. I'll just write it this way. 1 over log n is bigger than 1 over n, right? And the sum of the 1 over n diverges. So this log is one of these where we didn't necessarily ever give it its own sort of, hey, this guy always converges, but it does. Or, I'm sorry, always diverges. The sum of 1 over a log diverges. So in this, okay, harmonic series. Okay, what about when x is negative 1? What happens there? So what do you get in that numerator? Negative 3 to the n. Let's write this one out. So,
Negative.
so you cancel out the 3 to the n's, right? But that negative 1 to the n's left over. And so now what kind of series is left? Negative 1 to the n over log of n plus 2 is a alternating series. The terms go to 0, they're decreasing, and so it converges, right? Converges by the alternating series test. That make sense? And so now you got divergence at 5, convergence at negative 1, and so your interval goes from negative 1 to 5, diverge, converge, right? Be careful, both examples I did converged at the left and not at the right. It can converge on both ends, it can converge on the right and not the left, so just take your time when you're doing them and show all your work. Okay, like I said, for this next one, right, it's easier just to go ahead. So I said earlier that we always use the ratio test, but I lied to you, sorry. I'll try to lie to you less often. But the root test is just the exact same thing, right? And it'll work in the exact same way. And so you're either using the ratio test or the root test. So let's use the root test. So we take this thing here, we get absolute value of x to the n, n plus 1 to the n. Okay, taking the absolute value of that. So what happens now when I take the nth root of stuff being raised to the nth power? Yeah, cancel, right? The nth root of the nth power is just the original. So this becomes absolute value of x and then over n plus 1. All right, what is n plus 1, or what does that go to?
0.
Yeah, that just goes to 0, right? You got a fixed x, it's 1, and so what do we have? Yeah, so it's less than 0 from the root test means convergence, right? And so this doesn't matter what x is, it always converges, so your radius is infinity. And you don't need to write the interval in that case, but if you do, everything. Does that make sense? Okay. All right. Let's do this. All right. So here's a nice thing. So suppose this guy converges on an open interval I. Okay, so here's the theory. You've got a series and it converges on an interval I. The only reason we need to do the open is because you might get weird behavior at the open interval. So for instance, this series here that we just did, the x minus 2 to the n over this, remember it converged on this interval from -1 to 5, okay? When we apply this theorem, we're only going to be able to apply the theorem from the open interval from -1 to 5. Does that make sense? So that endpoint might lose whatever's happening there. So the theorem only works on closed intervals, but essentially, if you have a radius of convergence, the theorem says that everything works just fine as long as you stay inside your radius of convergence. It's just those endpoints where weird stuff can happen, okay? And so the theorem just says that you can take derivatives. So then f is differentiable, and better than just being differentiable, we can calculate the derivative by just doing the derivative at each point. Okay? So let me just write this up. This is c sub 0, c1 x minus a, c2 x minus a squared, c3 x minus a cubed, c4 x minus a to the fourth, and so on. So let's do a couple things. What's the derivative if all of the rest of this was gone and c4 was just some number? What's the derivative of c4 x minus a to the fourth with respect to a? So again, that's just a constant, right?
4c4.
Yeah, so the 4 falls out front, and then x minus a to the third. Does that make sense? And so if you think of that here, if you fix an n, right, and you think that's just a constant, that n falls out front, right, and so you'll get n c sub n x minus a to the n minus 1. And then the only other thing to consider here, what's the derivative of c0?
0.
It's 0, that's just a constant, right? And so the way we deal with that is rather than saying our derivative goes from 0 off, we drop our counter and say we're just going to start at 1 instead. Does that make sense? So that eliminates that first term. So this is, we say, so when we do this in the future, we'll say that you can differentiate power series term by term, right? So you can go inside. So basically the derivative slides past the sum and you take the derivative inside. Okay? Same thing holds with the integral. So the integral of f of x, I'm going to be lazy here. F of x is integrable, so it has an integral. And I should say differentiable on I. Right? So this is where that I comes into play. The derivative and the integral are only defined on that open interval. So usually we just find the radius of convergence and we say everything inside of that, we ignore the endpoints for this theorem. Okay, and so I'll just write it like this, right? Whenever you integrate, you get a constant. I just wrote it really big so that I just differentiate. You have a constant plus, and then you integrate term by term just like you did before. So I'll just do this. Sum from 0 to infinity. Again, let's just start with this fourth term here. What would I get if I integrated c sub 4 times x minus a to the fourth? Just over 5, right? X minus a to the fifth over 5, and then the c4 just sits there, right? You just add 1 to the power, divide by the new power. And so in general, if I have, oops, c sub n x minus a, it's just c sub n x minus a to the n plus 1 divided by that new power. Does that make sense? And so we'll make a lot of use of this theorem in the next section as we start sort of building a whole pile of functions that we can represent using series. But let's do one real straightforward example here. So actually, let's just do this 1 plus x squared times 2 factorial. Okay, so here's my function 1 plus x squared over 2. I say 2 factorial, but it's over 2. X cubed over 3 factorial, x to the fourth over 4 factorial, and so on. If I wanted to write that as a sum, what am I getting? It's just x to the,
And also plus 2.
well, if I start at 0, right, then it should be x to the n, because I got no x1. And then over just n factorial. And remember, 0 factorial is 1, so that this is really one of the places, that's why we sort of define 0 factorial to be 1, to make formulas like this work out nicely. But that's what you end up with. Does that make sense? So let's apply this theorem. Oh, let's first do this. Find the radius of convergence. Okay, I'll give you 20 seconds. This one should be really quick. You just do it in your head. Actually, I'm going to do it after the second. Alright, so if you just apply the ratio test, right, you should get absolute x over n plus 1, and what's that go to? 0, so what's your radius? Infinity. So this means that this function's defined for every x, right? So this is a function, it's defined for every x. Your interval is from negative infinity to infinity. That's an open interval, so the theorem applies. It's just saying no matter what you do, you can take the derivative of this function everywhere and you'll get the right thing. So now, let's take the derivative, and I want you to do this 2 ways. I know it can be a little bit tedious, but I want you to just look at the series written out this way and think about what the derivative looks like, right? And then look at it this way. This one I'm just going to do. So you should get that, right? The n just falls down. You can clean this up in a minute, but take the derivative of these term by term and see what you get. So what's the derivative of 1? 0. Derivative of x, 1. And then work your way across and see what you end up with.
Previous.
Oh, and this one should be 0, or should be 1, right? Drop that.
We are getting the previous Zero.
Right, good, good. So when you get 0, and then you get 1, and then the 2 cancels the 2 factorial, you get x. The 3 cancels, not the whole 3 factorial, but the 3, right? So you get x squared over 2 factorial, x cubed over 3 factorial, x to the 4th over 4 factorial, and so on. Right? And so that's exactly the same thing you started with, right? And so if you cancel this out on this side, right, you cancel the n and the n factorial, you'll get the sum from 1 to infinity of x to the n minus 1 over n minus 1 factorial. Again, maybe it looks different on the surface, but that's the same thing, right? Because if you plug in 1, you get 0 for your n minus 1. You plug in 1, you get 1. Or sorry, 2, you get 1. 3, you get 2, right? So you're getting the same thing, it's just written in a slightly different form. That make sense? So let's just say this. So f prime of x equals f of x. Now, you could guess what function that is. Everybody just had, or you had Calc 2 in the not too distant past. And so let me just remind you what you did at the end of Calc 2, right? We did a little bit on differential equations. And so if you had a function that looked like this, dy dx equals y, right? That's essentially what we have going on. F prime equals f of x. So dy dx equals there. Also look at that function. What do you get if you plug 0 in for x in that f? You just get 1, right? All the rest of it's gone. And so you get 1. And so now here's a Calc 2 problem at the end of Calc 2. Find the solutions to the differential equation, the derivative of y equals y, and y of 0 equals 1. You can probably guess the answer, but let's just work it out. This is a separable differential equation, very easily separable one. But you separate, and then you integrate, and remember doing this. What's the integral of 1 over y? dy? Natural log of absolute value of y, right? Derivative of 1 is x plus c. And then I'm going to just do some algebra here. You can e to both sides. You get that, right? And then this side you can rewrite as e to the c times e to the x. And then we can technically drop the absolute value if we replace e to the c with c. Because right, e to the c is always positive. And so if you just replace it with something that now can be negative, then you're done. And then if we plug in 0 and 1, we get a c of 1, right? And so we end up with our function must have been e to the x. Makes sense? So this series that we just wrote down over here, this is the series that represents e to the x. So we'll use that in the next section. We're going to start building up other examples of functions whose series we recognize. Does that make sense? Okay, well let's stop there.